Now we shall study about the different kinds of, we can say, restraining systems and how the structural steel beams are, we can say, constructed practically, considering that there may be flexural, torsional, buckling. So, first of all, we shall study about the different kinds of restraining systems for prevention of, we can say, flexural, torsional, buckling. So we can say it as flexural torsional buckling also, lateral torsional buckling also. So in some countries it is known as LTB, lateral torsional buckling. In some countries it is known as FTB, that is flexural torsional buckling. So we shall, first of all, we shall study about this particular behavior. That is, the beam may fail by flexural torsional buckling itself along this particular, we can say, axis. So the first and the most efficient system is that we can make it as a composite. So what we usually do, let us say this is the, we can say, top flange, this is the web, and this is the bottom flange. So we encase this particular structural steel beam in, we can say, RCC slab. So this RCC slab ensures that this particular, we can say, uh, top flange of this particular steel beam, it does not, get buckled. So that is one option. Second option is that we may add shear stud also. So these are known as the, we can say, shear studs. But again, that is, done where we can say uh, that behavior can be, constructed, we can say, by considering the composite beam behavior. So Australian and NZS, that basically has a different standard for the composite beam design standard, that is AS2327. So design of these kind of steel beams is considered in that particular code. So we shall be discussing this in great detail in a separate lecture regarding the design of, we can say, composite beams. After that, we may have seen, we can say, in the bridges, we can say, steel girders. In those bridges, we can say the depth is approximately 1500 mm. So it is something like this. Let us say we do have 3 to 4 girders. So this is the full road on the top of it where we have to, where the traffic shall be moving. So all of these girders, they are basically tied together with the help of these kind of angle sections. So these angle sections are like usually in the range of 100 by 100 by 8 or 150 by 150 by 8. So these angle ensures that these long, thin, slender, we can say, plate girders does not get bent or buckled in the case of what we can say lateral load, because ultimately if vehicles are moving over this particular road, there may be a lot of torsion, there may be a lot of eccentricity in the loading actions. So to consider those eccentricity and loading, irregular loading actions, we do provide these kind of, we can say, bracing arrangement to tie the whole system together. And if we draw this in plan, let us say these are the different 4 girders that we just made. So ultimately, what we can say is that starting point has to be, we can say, braced, end point has to be braced, this particular arrangement, and periodically we can add these kind of bracing arrangement. So if we draw a section from this particular area, it shall be looking something like this. The same shall be the case here also. So that is the, we can say, options for, we can say, restraining system for lateral torsional buckling. After that, we can study about the, we can say, what are the meaning of the full restraint. So we have studied in the early lecture about FPLNU, that is full, partial, lateral, and unrestrained arrangement. So if we're talking about the full restraint for beams, so that can be provided either, let us say, this is the beam that is being restrained. So from that we can, in the workshop we can weld a plate, and let us say we do have these HSFG, that is high strength friction grip bolts. We shall be discussing about these bolts also in the connection lectures. But as of now, you can understand that, let us say this is the beam that needs to be restrained, and this is getting connected with the help of the secondary beam here. So this is one example where we can say that this beam is fully restrained. And after that, we do have other options also. Let us say this is the particular steel beam, and we can, join the particular secondary beam like this also. Although, I definitely want to say that this kind of arrangement is rarely used. In majority of the cases, it is mostly used. So we can have this kind of, system as the fully restrained. Or what we can do is that, uh, let us say this is the particular steel beam on which we are studying about the restraining system. So what we can do is that we can tie an angle also, join this with this particular web, and we can do the welding here also. So this is another arrangement, alternate arrangement, where we can say that this is also a fully restrained system. So after that, another option can be like, let us say we do have this particular steel beam, which is like we can say continuously rested on a very particular like a fixed supporting system. And here we have provided either anchor fasteners or anchor bolts, and we do have a bearing stiffener also. So bearing stiffener is the one that is usually provided at the end. Let us say this is the girder, and this is the like center web, and if it is placed on some particular RCC pad here, so bearing stiffener is usually provided because there is a large amount of shear force at this particular supporting point. So to avoid the, we can say, warping or bending of the steel member at the edges, or to prevent the uplifting, it is usually made torsionally rigid by providing these bearing stiffeners. And one more arrangement, that is most commonly used is with the fly bracing. So what we usually do in that case is that, let us say this is the particular steel girder, and on the top of that we are providing a purlin section. So these purlin sections are usually cold form section. These are either in the this particular shape, that is Z shape, or we can say C shape. So these are the purlins which are usually tied together with the help of this fly bracing at regular intervals. So these fly bracing, either that can be provided on one side or both sides. So this section, it can be purlin also and girt also. So now let us say this is the steel warehouse building on which we are designing, or we can say understanding the behavior. So whatever purlins are fixed or at the top, they are known as the purlins. But whatever system we are providing at the sides to support the side sheeting, they are known as girts. So that is the difference between purlin and girt. So this is also like a system where we can say that these are the fully restrained beam. So we do provide usually a cleat also here, or L angle, and with these two bolts, so that we can easily fix, because purlins and girt, these are cold form sections of, let us say, 1.2 mm thickness, or we can say 2 mm thickness, which cannot be welded. We do need to understand that these purlins are never welded to the steel beams. They are usually bolted only because the thickness is not that much. So even if you provide, even if you do the welding, it has to be replaced because this metal get burnt at the time of the welding. So that is the one example of, we can say, fully restrained beam. After that, we can understand the partial restraint of beams also. Partial restraint of beams. So if we are talking about the partial restraint of beams, so let us say we do have this particular steel eye girder, and on the basically right hand side we do are providing the steel beam, and here we do have a flexible end plate, that is, it can allow the rotation. So this is the example of the partial restraint. Second example like can be that let us say this is the particular steel beam, and on the bottom of that we are providing an angle. So this is also partial restraint because the top flange is usually free in that case. So similarly, there are other examples also. Let us say we do have like a face column here, and on the face of the column we are fixing this particular steel beam with the help of these kind of two angle systems, and which is getting connected with the help of the high strength friction grip bolt. So this is also an example of the partial restraint. Another example for the what we can say is lateral restraint. Third, we shall study about the L, that is the lateral restraint for beams. So one of the example is that we are fixing these steel beams, and on the top of that we do provide a checkered plate. So checkered plate is the what we can say a plate that is most commonly used in the industrial steel structures across the whole world. So that plate usually has a corrugation on the top of that to ensure that whichever person is walking on that plate, that does not get slipped, and obviously it also helps in increasing the strength and stiffness. So they are usually in the range of 5 mm, 6 mm. 6 mm is the one that is most commonly used. 8 mm is also used, but obviously that is quite expensive and heavy also. So in majority of the cases we do ensure that we do plan or align our structural shear arrangement to allow the 6 mm thick checkered plate to be installed. What I'm trying to convey is that let us say we do want to have a particular structural steel arrangement, and we do need to plan our secondary beams which are supporting the checkered plate. So let us say these are the main beams, and inside we do have the secondary beams. So we do ensure that the spacing, let us say if the plate is of 6 mm, we do ensure that the spacing does not exceed, we can say 750 mm or 800 mm. Because ultimately, if we are providing 6 mm thick checkered plate between the spacing of let us say 1500 mm, then plate itself get bent when someone shall walk on that. So there is a restrictive spacing for a particular thickness of the checkered plate. On the basis of that, we do need to plan and design our structures. After that, we can study about the lateral rotational restraints. So if we are talking about the lateral torsional restraint, let us say we do have we can say face of this particular steel column on which we are fixing this particular steel I-beam. So in here, let us say we do have a vertical plate projecting out of it. Let us say this is the steel column, and here we do have this particular steel plate from which we are fixing this particular steel beam. The help of these bolts. So this is like one example of lateral rotational restraint of the beam. The second example can be that let us say we do have this particular steel column on the top of which we do have fixed a bearing plate, and on top of that we have rested our beam. So this is also like another classic example of the lateral rotational restraint for the beams. So with this, these are the different examples in which with which we can plan what exactly are the different kinds of the rotational restraint for the beams. So on the basis of that, we do fix our three different parameters, the three kings which determine the capacity for the the capacity for the laterally unsupported beams. KT is the twist to strain factor, KL is the load height factor, and KR is the lateral rotational restraint factor. So these are the different factors basically which do determines that how and what are the different values. So let us just study about these values also, that is the default values of KT, KL and KR for different, we can say arrangement. So first of all, if we are talking about the the reason for calculating this is that basically they all are multiplied together to find out the effective length. The effective length of the beam LE is nothing. LE is equal to KT, KL, KR multiplied with the L. That is the center to center of the beam. Let us say this is the beam and center to center is approximately 8 meters. So it is not that we can simply consider this 8 meter in our calculation. We do have to multiply this with KT, KL and KR. Only then we can find out the effective length of a particular steel beam. So first of all, if we are talking about the different values, so we can scroll down here. Yeah. So first of all, let us say the direction of the action load and the flange on which it acts. So that also determines the KT, KL and KR factor. So let us say if we are talking about the case 1 and case 2. So it shall be better if we can open the code itself where it is guiding us regarding the different values for the KT, KL and KR. So these are the factors that are given in AS 4100. So for considering twist restraint factor KT, we as per the restraining arrangement, that is FF, FL, LL and FU. So F is basically the fully restrained, L is basically the lateral restraint, U is unrestrained and P is partial restraint. So these are the end conditions. So FF means fully restrained at the start, fully restrained at the end. FL means fully restrained at the start but laterally restrained at the end. LL means the lateral restrained at the starting point also and lateral restraining at the end point also. And FU means fully restrained at the start and unrestrained at the end. So for all of these factors, KT is basically 1. Similarly, for other arrangement, let us FP, FL, FP, L and PU, you can understand that partial restrained and unrestrained. So starting at the starting point, it is partially restrained and the end point, it is unrestrained. So for that, we do have this particular formula to calculate the value of the KT. And for PP means partially restrained at both the ends. So similarly, we can find out the value of the KL also, that is load height factor for the gravity loads. So if the load is at basically the shear center, which I have said that is like quite uncommon. So for that it is 1, but in majority of the cases the load is at the top flange. So that is why in ETABS also by default this value is 1.4. So that we shall discuss in detail when we are modeling this particular steel beam in the ETABS software also. So similarly, if we are talking about the within segment, it is this particular value, but at the segment end, that is the longitudinal position of the load. So in that case, it is basically 1 if you're talking about the supporting condition. And if you're talking about the unrestrained supporting condition, that is FU and PU. Fully restrained at the start or partial restrained at the start, but unrestrained at the end, it is 2. So similarly, we can find out the value of the KR also, that is lateral restraint factor. So FU and PU, the factor is KR, that is the maximum value. But if it is fully restrained at starting point and end point, this value is the minimum, that is 0.7. So if we know that our beam is fully restrained at the starting point and end point also, we can decrease the bending moment capacity requirements by considering the KR as 0.7, which by default is in ETABS as 1.0. So that is the language of the code. That is F is fully restrained, L is laterally, P is partial, and U is unrestrained. So that is the language of the what we can say code itself. But if we want to study, or we can say we can have simplified values also that we can simply refer. So the simplified values are, as we were discussing, that here it is case 1. So if the action load, this is KT, KL and KR. KT, KL and KR. So if basically the action load is acting downward on the top flange, so if the load is acting downwards on the top flange, we can simply have KT value is 1.1, KL value is 1.4, KR value is 1.0. And if the load is acting at the shear center, that is, this is basically the shear center and the load is acting here, which I said that is quite uncommon. The KT value is again 1.1, KL value is 1.0 and KR value is again 1.0. So these are the values considering that we're talking about the simple beams And we are okay with a little bit of conservative values also. So on the basis of what we can say simple beam assumption and on the application of the loading point on the steel beams, we can simply find out the values of the KT, KL and KR. So if we are talking about if we are talking about the beams which are supported at both the ends, but if we are talking about the cantilever beams, the values of the KT, KL and KR are a little bit higher. So if the beam is something like this and the load is acting on the top flange, the values of what we can say KT, KL and KR. So the value of the KT in that case is 1.1, KL is 2.0 and KR is again 1.0. And if the load is acting again at the shear center, which I said that is like very, very uncommon, or if the load is acting on the bottom flange also. So in that case, KT is 1.1, KL is 1.0, and KR is again 1.0. So that is the different values which we can take when we are designing the steel beams and we want to calculate the value of the KT, KL and KR. So I hope this lecture is clear to you that how the meaning of F, P, L and U. And if we are talking about FF, it means that the beam is fully restrained at the starting point also, and the beam is fully restrained at the end point also. Similarly, if we are talking about the FP, it means that the beam is fully restrained at the start and partial restrained at the end. And we have discussed in detail also regarding by drawing the practical sketches of what exactly are the meaning of F, P, L, and U, and how we can assign them or consider them in our practical calculations.